Hello, everyone. Thank you for attending today's webinar, which is the first installment of the UESI Best Papers webinar series. The series focuses on covering honorable mentions and candidates for the best paper across the UESI Pipelines Conference, meaning if you attend this year's conference taking place in Tampa, Florida from August 9th to August 13th, you can get a preview of what's to come for webinars. My name is Rihanna, and I'm the Marketing Communications Coordinator for UESI. I'll be handling the technology side of the webinar, but before we start, as this is going to be a more interactive webinar, just want to encourage everyone to chat amongst each other with the chat function. But please, if you have a specific question, to direct your questions to the Q&A bubble. You can find that in the toolbar at the top next to the chat icon that says Q&A. And once you head into the Q&A, there will be another little chat bubble next to the gear icon. If you click on that, you'll see options to either start a discussion or ask a question. So if you start a discussion, for example, you will likely see that published. Whereas if you ask a question, we will be able to view that more directly and be able to see that as a higher priority. We really do prefer that you hit ask a question if you would like to ask a question during this presentation, and please just select that before submitting anything. You can also raise your hand. With that, I'd like to introduce our moderator for this webinar series, Kyle Couture. Kyle is a mechanical engineer with 27 years of experience in sales, project management, and marketing within the water and wastewater industry. A nationally recognized project manager for steel water pipe projects, Kyle has held various leadership roles at American Cast Iron Pipe Company, where he currently serves as the marketing services manager. Throughout his tenure at American Cast Iron Pipe, Kyle has successfully led teams and driven projects in diverse capacities, and he's been a member of ASCE since 2002, serving in various roles and capacities. Thanks for being on, Kyle. Glad that we can have you on with us, and feel free to take it away.
Thank you very much, Rihanna. Thank you, everyone, for being here for our UESI Best Paper webinar. So we're joined today with our presenter, Inshik Park, and he's also known as Justin Park. You'll see his name on the screen today as Justin. A little bit about Inshik. He's a PhD candidate and a graduate research assistant in the underground trenchless construction program at the University of Alberta under the supervision of Dr. Ali Bayat. He's also a graduate teaching assistant at the Department of Civil and Environmental Engineering, and he has been involved in teaching undergraduate and graduate courses at the University of Alberta. Inshik's research focuses on the geotechnical aspects of horizontal directional drilling, the subject of today's presentation. For the UESI Pipelines conferences in 2024 and 25, Inshik has served on the Technical Program Committee as a technical reviewer moderator. He's also a peer reviewer of the Journal of Pipeline Systems Engineering and Practice. Inshik is a winner of the UESI Pipelines Conference Student Scholarship in both 2021 and 24, and is currently an active member of the UESI Younger Member Engagement Committee. So we're looking very forward to having Justin present to us today. As moderator, you'll probably hear me kind of interject a little bit so I can see if Justin would elaborate on some of the topics that he covers today. But at this point, I'll pass it over to Inshik.
Thank you very much, Kyle and Rihanna, for helping to moderate and organizing this event. And I'm going to share my screen here. So it's right here. Can everybody see my screen?
Yes.
Okay, sounds good. So again, my name is Inshik, and I'm the presenter of today's webinar. And I would like to acknowledge UESI for giving me opportunity to present my study at the Lunch and Learn. And today's presentation is called Introduction of the Concept of Probabilistic Risk Assessment for Evaluating the Borehole Stability in Horizontal Directional Drilling. So it's a long name. And so Kyle already introduced me, so I'm going to skip my introduction in here because it's going to be repeating. And for today's presentation, it's going to start with the background information, and then I'm going to state the problem that I found during my study. And I'm going to talk about some probabilistic method is used in other discipline of geotechnical engineering and with some conceptual explanations related to that. And then I'm going to relate that to what it happens in horizontal directional drilling and its hydraulic fracture analysis. And then I'm going to talk a little bit about the consequence of failure and the risk evaluation. And I'm going to apply those concepts to show how it can be applied in the case study of HDD. And lastly, I will list some future direction. And Kyle, if you have any question you want to address in the middle, you can let me know, and then I will answer your question.
Sure, will do.
So to start with, let's talk about the trenchless and horizontal directional drilling itself. So when we have an urban area with a lot of people living in there, we definitely need some resources to be transported, such as water, or oil and gas, and there's more. And for doing that to transport from location A to B, we typically need some infrastructure like pipelines to be installed. Typical procedure to install the pipeline is either bringing heavy equipment or use the direct manpower, and then we will excavate trench, and then we're going to place some pipe beddings and then install our pipe, and then backfill and compact, and we will reach all the way to the surface. And this is typically called open cut trenching method. This method has been used in almost like many projects in the pipeline projects over the human history. But there are some situations it's difficult to apply. Like, for example, this is the New York downtown. And as you can see already, there's so many underground utilities existing there. If you're looking at it here, between the buildings, there's many wires and conduits there. So if you try to excavate and then place your pipe and try to backfill and compact, that is going to be very challenging and nearly impossible. So for those cases where there's many existing utilities existing, then actually the options like trenchless could be good item to think about for those cases, because instead of making open cut trench, these are trenchless techniques, so you can drill horizontal boreholes that can be used as installation path for the pipelines. And not only for urban areas, but it's useful in river crossings or highway crossings or railway crossings where it's difficult to excavate trench, then trenchless is a good option for many cases. And I will talk a little bit more about the horizontal directional drilling, how it works. So the first step, when we spot some surface obstruction, then we would like to determine either entry point and the exit points. And then we will put our HDD rig. Horizontal directional drilling is often called as HDD. So we will put HDD rig, and then we will start drilling our initial borehole. It's called a pilot bore. So usually this initial borehole is small. It's about 4 to 12 inches diameter. And these boreholes are important because it set up the path for the further drilling for enlarging the borehole. So the next step and the direction of drilling start from the rig, from the entry side toward the exit point. And the next step, once the pilot bore is prepared, what we do is enlarging that pilot bore to the final size of the borehole that's required for installing our product pipe. We typically use something called reamer, or other name it's called hole opener. So these are the cutters. They can be attached at the tail string and be pulled by the directional drilling rig, or they can be attached to the front of the rig and it can be pushed rimmed. So the direction of reaming can happen both toward the exit and the entry side. And depending on the difference between the final size of the borehole and the initial borehole, these reaming passes can be multiple times. And lastly, when our final borehole is prepared, what we will do is something called pullback of the product pipe. So we will attach the product pipe to the drill string, and then we're going to start pulling in the product pipe into our borehole. And when the product pipe reaches all the way to the entry site, and then the installation is going to complete. So the direction of the pullback will be from exit site and toward the entry side. So when we try to create the borehole, we typically generate something called drill cuttings. It is the cuttings of the earth material happens due to the activities at the drill end. And these are usually required to be removed out from the borehole in order to have our have our installation borehole to be prepared. And to get rid of those drill cuttings, we typically use something called drilling fluid. It is a mixture of water, bentonite, and mixed with drill cuttings, and typically some additives depending on the situation. And those drill fluids are typically filled up with pressure because, and then it's filled up with pressure. This pressure is called the annular pressure because this is the pressure of drilling fluid within the annular space of the HDD borehole. And there are two different types of annular pressure. The first one is called minimum annular pressure required for circulation, or we often call it as Pmin. Or the other one is called the maximum allowable annular pressure, or we call it formation limit pressure, or simply call it as Pmax. The reason we apply pressure in drilling fluid is because, first of all, we would like to provide some hydraulic power to the downhole mud motor. So these pressures are converted mechanically to be able to rotate our drill bit at the drill end. And the next one is we ensure the transportation of the drill cuttings. So we remove the drill cuttings using the pressure of the drill fluid. And the last one is ensure the stability of borehole because we're creating empty space in the underground. So if we do not fill it up and support it, the borehole is likely to collapse. So in order to prevent that, we need to match at least the in-situ stress of the ground condition. So that's why we apply some pressure for the stability of the borehole. And this annular pressure is going to increase when we drill further from the entry location. The reason is because let's imagine we are trying to get rid of the drill cuttings near the entry site. Then the distance it has to overcome is not so much. In comparison, when we have drill cutting almost at the end of the borehole, the distance it has to travel is much longer. And that means it has much longer distance. It has to overcome the frictional resistance exerted by the wall of the borehole. And when this pressure required for circulation, Pmin, exceed the maximum capacity of the borehole, Pmax, then it is likely that borehole may fail and hydraulic fracture can occur. That means that the drilling fluid inside the borehole can no longer be contained within the borehole, so it will start escaping toward the surrounding environment, or it can reach all the way to the surface. So here's the example photo that the drill fluid was found at the surface. And if that happens in the roadway, then it's quite problematic because the incoming traffic, their safety could be endangered because this drill fluid is slippery material, so it can cause vehicular accident. So in that case, it needs immediate cleanup, and also it has to apply some frictional material like sand to make the road more safe. And if that happens in the urban settings, then if there's the pressure applied toward the surface, it can actually uplift the surface structure and it can damage what's on top of it. And if that happens near the culverts or creeks, then you can see the drill fluid is contaminating the water. And if that happens some important infrastructure, what you're seeing here is the embankment, dams, and levees for flooding control, then the regulators may not be very happy about it. And if this happens in the environmentally sensitive areas like wetland, as you can see, creates a lot of mess, and the remediation is going to be time-taking and costly. And not only adverse for environment, but if the drill fluid cannot be contained within the borehole, that means we may get into a whole cleaning issue. And when we try to pull in our product pipe into uncleaned borehole, there's a high chance that HDD installation could fail. And from our case study with 100 HDD projects, we found about 2/3 of scheduled delays are somehow related to either drilling fluid or annular pressure. So that means it is critically important we have proper management of drilling fluid pressure during HDD. And according to ASCE's MOP 108, which discusses about the HDD design, the risk of inadvertent return, or IR, could be increased by following condition. It's called inadvertent return because when the frac out happens, the drill fluid is not returned to the either entry pit or the exit pit as we want. So there's some kind of inadvertent return happening, and that's what it's called for this type of risk. So I kind of grouped them, the items they listed together. The first group is related to ground condition. So when there's a very loose or soft formation existing, so the ground adjacent to HDD borehole is too weak, so it's easy to cause the frac out. If there's clay formation with high swelling potential, that means this clay is quite sensitive to moisture. So when water or drilling fluid is introduced to it, it's easy to expand. That means if we have a borehole like this, it can actually expand and make the annular space much smaller. So it can cause either borehole squeezing or it can cause hydrolocking. And with the reduced area, it's easy to spike the annular pressure, which means it's easy to frac out. And if there's ground condition with is highly permeable due to various reasons, like for example, like granular soil with large openings, or bedrocks with fractures, or any type of like piles or foundations or existing utilities which provides the preferential flow path, then it's easy to have the drill fluid to flow into those locations and be lost. And if there's some spatially varied condition or mixed interface transition zones, it's easy to have the drill fluid flow into the transition zone, or because it's spatially varied, the strength and the resistance of the ground may vary, so it's difficult to maintain the consistent annular pressure. So that's going to be problematic when we try to prevent a frac out. Another group is related to bore geometry. So one example is when we do not have sufficient cover. So above the borehole, we do not have much cover to provide the confinement, so it's easy to cause the frac out. Another one is when we have considerable elevation difference. So when we have situation, we're drilling from uphill, and then when we reach all the way downhill, because of the hydrostatic pressure is pretty high, we're going to utilize high annular pressure easily. Then it is also the situation is easy to frac out. And the other group is related to construction itself. So when we use inappropriate downhole tooling or drilling practices, let's say our drilling is not very efficient with the tooling we selected, or if we're going too fast, or if we're utilizing way too high pressure, then those are the situation. It's easier to frac out as well. And when the circulation of drill fluid is being lost or severely diminished, so at the entry or the exit pit, when we do not see the return of the drilling fluid, that means that's an important sign there could be some kind of IR happening in somewhere that we didn't spot it yet. So in order to prevent this type of risk, we conduct something called hydraulic fracture analysis. And related to that, ASCE-MOP specifies that engineering judgments and experience must be applied in utilizing hydrofracture models to predict the occurrence and non-occurrence of inadvertent returns. So it doesn't specify too much about which model and the method we have to select. And I believe it's because depending on which region, type of the soil is different and the model it works could be varied. So it kind of asks us to make sure we have sufficient experience to make good engineering judgment.
And Chuck, let me interrupt you for a second on that. A question I have, it seems that IR is very dependent on your Pmin and your Pmax.
Yeah.
When are those values typically known in an HDD?
So Pmin and Pmax, we can both determine them from the design phase. And so that is the design parameter. And what we also have to confirm is how it works at the construction stage, right? So we have measurements, we can see if our pressure is matching the Pmin, and those Pmin, Pmax usually Pmin can be assumed with some drill fluid properties, those rheological parameters. Like it could be dependent on who's constructing it as well, but from design we can kind of predict based on what the formation is like and what is the effective like hole cleaning parameters we can utilize. And for Pmax, we will get it based on the geotechnical information we collect at the design stage. Okay, then I will continue my presentation. So in order to conduct the hydraulic fracture analysis, typically what we do is the method suggested by Bennett and Wallen in 2008. They introduced this method in Pipeline Conference. And the basic idea is creating 4 different curves along the HDD bore path. The first one is the ground surface, so it shows the topography of the HDD site. And the next one is the bore elevation, which represents the HDD bore path. Then the next one is the Pmin curve, shows the minimum annular pressure required for circulation. And the other one is the maximum allowable annular pressure, or Pmax curve, so it shows the upper limit of the ground before the failure. So the basic idea about this method is making comparison between the Pmin and the Pmax along the HDD bore path. And this method is used in almost every HDD design nowadays. And it's actually graphically very easy to understand where it has low risk or high risk of frag out. And here's the problem that I found during my study related to this method. This method is very useful, but in my opinion, I think the method is a little bit too deterministic rather than sufficiently considering all the uncertainties related to underground drilling. To make it easier, let's imagine an HDD bore path that crosses various ground material. That means we may encounter material with different properties, and that means we might have to consider different recipe for drilling fluid, and we might have to use different toolings as well. And while there are so many uncertainties existing, I am not sure if the current way of conducting hydraulic fracture analysis can take everything into account. And talking about uncertainty, according to Dr. Morgenstern at the U of A, there are multiple sources of uncertainties in geotechnical engineering. The first one is called parameter uncertainty. So when we have mathematical model to predict something, we need some input parameters. And depending on if the parameters have some error, it can actually cause some error in the results of the analysis as well. So this is called parameter uncertainty. The next one is called the model uncertainty. So those mathematical models we use, if they deviate from the real phenomenon, it can also cause the error in the analysis. So that is called model uncertainty. Another one is called the human uncertainty. Dr. Morgenstern recently mentioned this is also called as human ignorance. So depending on who's practicing it, the level of knowledge and experience can be different. And that's actually related to what ASE MOP was describing. We need sufficient experience to have better engineering judgment. So those type of judgments, if we do not make it adequate because of lack of experience and knowledge, and that can be another source of error, which is the human uncertainty. And now let's talk about each uncertainty in a little bit more detail related to HDD. So for now, we're going to talk about model uncertainty first. When we conduct hydraulic fracture analysis and need to predict Pmin and Pmax, for Pmin, we have multiple models available to predict. In comparison for Pmax, we really have many models available in the literature. And I went through all of them, and I think each of them make their own sense. But current stage, there's not enough data in the literature to say which one works superior to another in which situation. And for designer perspective, it's actually quite confusing. And now let's talk about model uncertainty. I mean the parameter uncertainty. So what you are seeing here is the HDD bore path within a ground condition, something called glacial ground moraine. So in this type of glacial material, you can expect all different type of materials such as gravel, clay, silt, and the sand. So when you are drilling, you are going to encounter all those in various locations. And when you conduct the hydraulic fracture analysis, you need to obtain some geotechnical parameters, such as stress state parameters related to like unit weight and lateral earth pressure coefficient. You also need strength related parameters, such as cohesion, internal friction angle, under and shear strength. And you also need stiffness-related parameters such as modulus of elasticity, shear modulus, Poisson's ratio. And then how we determine them is we will base them on geotechnical exploratory boreholes. And one interesting thing here is you can see those geotechnical boreholes are kind of congested near the entry and the exit sites, and there's not much going on in the middle. And I'm thinking the reason is because there's a bridge right there, so it was more difficult to have geotechnical boreholes nearby. And I'm thinking that could be the reason they decided to go for trenchless as well. But one fact it doesn't change is near the geotechnical boreholes, we're more certain about the geotechnical parameters. But when we get further from those boreholes, we will be less certain about it. So there's many uncertainties existing in geotechnical engineering like this. And in order to deal with those uncertainties, typically we consider something called a probabilistic method. So in the next portion, I will show you what the probabilistic method is being used in other geotechnical disciplines. For example, in here is the slope stability analysis.
Hey, Justin, Insha, can I interrupt you one more time?
Go ahead, Kyle.
Sure. Is it typical practice when you have the variation in the geotechnical information to utilize somewhat of the worst case scenario to determine your Pmax?
Yes, that's one way. That's what a lot of practitioners I see from literature they like to do. They don't want to have like a parameter that's unconservative. And so usually how they do is they either have direct measurements or they can also have empirical determination. So based on the experience with that soil, they have range of the values they can select. And it is a common practice they will try to be conservative, but it's actually also, as what I mentioned, it's based on the judgment. It's not like a structural design. There's like a code and then certain value you have to use, and it's like fixed procedure. It's more like up to us, like what we have to decide, and it will also depend on who's deciding that. There could be some debate between what parameter and what magnitude they want to choose.
Okay, that makes sense. Thank you.
Thank you. And yeah, that actually gets to the core point of today's presentation as well. So I will relate that in the later slides. So when we try to evaluate the stability of the slope like this, I will try to explain in the simple way. What we usually do is we will assume a failure surface, and there will be kind of two different type of forces acting on it. One is the force exerted by the sliding mass that is trying to slide down toward the downslope. And another type of force is the force resisted by another side of the ground. So the other side of the ground is trying to hold up the sliding mass. So the factor of safety will be the concept, or it will be the comparison between these two forces. And if the factor of safety is greater than 1, then the slope is going to be considered stable. If the factor of safety is equal to 1, that slope may be considered right at the edge of failure. And if the factor of safety is less than 1, then that slope has a high chance of failure. And now I'm going to show you how the probabilistic method can be used in this type of analysis. So the first thing is they will also deal with the parameters. What you are seeing in here is the collection of geotechnical parameters within the area of study. Example in here is showing the effective friction angle, and y-axis is showing the probability. So if they decided to go for deterministic approach and get a single value of factor of safety, then maybe they would choose average value, such as like 38 degrees in here, which is the most common, or they would choose a little bit more conservative value to be on the safe side. But when we are conducting probabilistic method, we will rather consider the entire data and what's the pattern of it. So the first thing we will do, we will create a histogram like this, and we will determine the most representative probability distribution function. So it can actually represent the shape of diagram. So we would like to consider the entire data to the further analysis. And in here, they chose log normal function in this case. And next step they will do is they will carry on those input distributions, and then they will apply them to models. Models can be either analytical or numerical. So those are kind of like a limit equilibrium equation, like a hand calculation. And the other one is kind of like a software using the finite element method or discrete element method. And the next step they will do is handle the model uncertainty. The first group is talking about considering partial factors to input parameters. So depending on the sensitivity of parameters, they can consider different magnitude for those partial factors for input parameters. Another way they can do is depending on the tendency of the model, either under predicting or over predicting, they can choose a global model and consider the correction factor to each cases. So once model and the parameters are determined, what they can do is something called integration. So the basic idea is repeating the calculation of factor of safety while you're varying the input parameters randomly. It's random, but not entirely random, because you will still follow the input distribution curves. And as a result, for integration, there's multiple ways of doing it. So there's first order, second moment method, second order, second moment method, point estimate method, and Monte Carlo method. And as a result, what you will get is the distribution of factor of safety. And under this factor of safety distribution, where the factor of safety is below 1, the area is going to be considered probability of failure. And this is an important index used for the further risk evaluation. Another index used often is called the reliability index. So this is kind of a brief concept of how they determine the probability of failure in this type of geotechnical practice. And now I will relate that to our HDD. Coming back to HDD, we have two different types of annular pressure as well, which is the Pmin and a Pmax. So there's no reason we can do something similar. The factor of safety will be the ratio between Pmax and the Pmin. And if the factor of safety is greater than 1, then the borehole is likely to be stable. If the factor of safety is equal to 1, then the borehole may be at the edge of failure. And if the factor of safety is less than 1, then the borehole may fail and hydraulic fracture can occur. So there's no reason we can apply similar method of the probabilistic approach. And I'm going to show you more details in the further section using the case study. And for a bit of time, let's talk about the consequence of failure and risk evaluation. For consequence of failure, let's say there's a slope failure, and then there's multiple things get affected, which is called PAP, which stands for people, environment, asset, and production. When the slope fail and then there's people living nearby, it can endanger the safety of the people's life. And if the large ground mass slide down and then change the topography, it will affect the environment. And also, if there's houses or infrastructures near those slopes, it can adversely damage the assets. And if that's the case of mining operation, let's say there's open mining, open pit mining, and there's like workbenches fail, or if that's the case of tailing dams fail, then it's going to affect the mining operation and its production. And for a case of HDD, if blackout happen, it also affects multiple things. We had the example if it happens in the roadway and the drill fluid is released to the surface, and it can endanger the driver's safety. If that happens and release the drilling fluid to the sensitive environment, then that's going to cause environmental issue. And you can see the surface structure could be damaged, so it's the asset problem as well. And we saw if whole cleaning can be like affected, and it can actually affect the production rate of the pipe installation as well. So once the probability and consequence are determined, what we can do is something called risk evaluation based on the predetermined risk criteria. So where the probability and consequence are both low, that is going to be considered low risk. And where the probability and consequence are both high, that is going to be considered high risk. And there will be maximum envelope how much they can take the risk. So before that point, it's going to be acceptable risk, and beyond that, it's going to be unacceptable. And depending on who's taking that risk envelope can be varied because everybody have different tastes of risk. Excuse me. And another important term I would like to highlight is called ALARP, which is as low as reasonably practicable. So I'm thinking for HDD and hydraulic fracture, we also need an envelope that is reasonable and practicable. for our HDD design. And now let's move on to a case study with a virtual HDD bore path within decomposed bedrock. So for those of you who's not familiar with what decomposed bedrock is, it's kind of a weathered bedrock. So it could be either fully decomposed into like a clay material, or it could be just slightly fractured, or it could be heavily fractured. So in this type of material, spatial variation could be expected. Let's say the HDD bore path is 300 meter long and 10 meter depth. And we can imagine that HDD bore path is designed based on geotechnical boreholes. Here are the locations of them. And let's say they have some in situ test measurement like SPT or laboratory tests like UCS. And here are the points of interest for the further analysis. And this is the geotechnical information that I use for this analysis. As you can see, only the 2 points are directly related to that HDD, but it is typical we utilize larger group of data from the entire pipeline project to have a better understanding of the material. And when we conduct the traditional way of hydraulic fracture analysis, it will come out something like this. So we have both Pmin and the Pmax curve. So for position A, you can see Pmin and Pmax are very close. Actually, for this case, Pmin is slightly higher. And for position B, we can see Pmax is much higher than the Pmin, so the risk of frac out is low in here. And for position C and D, we can see Pmin is much higher than the Pmax. So for those cases, risk of frac out is much higher. And when I conduct a probabilistic analysis for position A, it will look like something like this. It looks like a lot of information. I will make sure to explain one by one. So the first setting here is the geometry of the borehole that I inputted. And there's 3 critical points that I considered for input parameters. It's because for all the input parameters, I consider the triangular distribution for the simplicity for explaining the concept. So for those of you who think you have a better idea which distribution to be used, such as like log normal for previous example, later you can try with those type of distributions. But for now in here, I consider the triangular distributions for all the input parameters. So those 3 critical points include the most likely value, lowest possible value, and the highest possible value. And this Fm is the shape function, shows the skewness of this distribution. And I use the random command using Excel, which generates the random variables between 0 and 1. And here are the mathematical functions, how I utilize this random command to randomly generate the input parameters. And those input parameters include unit weight of ground material, undrained shear strength, and I was able to get Pmax, and the unit weight of drilling fluid, yield point, and plastic viscosity, flow rate, and then I was able to calculate Pmin. And when both Pmin and Pmax calculated, I could get the factor of safety. And then I repeated that calculation for many times. So as result, it will look like something like this. For each locations, we're going to get different distribution of factor of safety. And for where factor of safety is less than 1, that portion is going to be considered probability of failure. So for position A, as you saw, Pmin and Pmax were very close. We get about 17%. For position B, where Pmax was much higher, the probability of failure is 0. For position C and D, where Pmin was much higher than the Pmax, we can see the probability of failure is 100%. So that is how you get the probability of failure. And I'm going to show you a few discussions that I considered. The first one was I was questioning how many number of runs is practical. So for position A, I tried 10 runs, 100 runs, 1,000 runs, and 10,000 runs. So for each number of runs, I got different probability of failure. But above 1,000 runs, I started seeing consistency, and that kind of matches with what the literature say. And that's the reason I decided to go for 10,000 times. And I think for this type of analysis, you need to consider at least 1,000 runs. And another one is I want to show you why we have to really consider the probabilistic method and what can benefit from this type of application. So that previous case study with the HDD bore path, you can kind of consider that risk of fractal is pretty high. If that's the case, usually what they can consider, if possible, then they will consider a deeper bore path to provide better confinement for the annular pressure. So now we have a longer and deeper HDD bore path, and the points of interest are newly defined. And when we conduct the traditional way of hydraulic fracture analysis, it will come out something like this. We have both Pmin and Pmax curves as well. So for position A, you can see still close, but now you can clearly see the Pmax is higher than the Pmin. And for position B, Pmax is still higher. And position C and D, Pmin is still higher, but you can see the gap is a little bit closer. So if we conclude our analysis in here, we would think the probability of failure at position A has been lowered. But when we conducted probabilistic analysis, actually that wasn't the case. Now the probability of failure is increased to 29%, while the previous shallower bore path was 17%. And that's because our soil strength distribution has become wider. When we were trying to deepen our bore path, we were actually getting closer to weaker strata, still closer to the stronger material, but there was an increased chance of having weaker material. And that portion of the wider range actually contributed the increase in probability of failure, and which could not be captured by the traditional way of hydraulic fracture analysis. And in here, I'm not trying to say we do not have to conduct the existing traditional way of hydraulic fracture analysis. But what I would like to emphasize is we're just introducing one more parameter. It's called the probability of failure. And it shows the influence of the uncertainties within the input parameters. And I'm thinking this additional insight is actually useful for consider when we try to determine our HDD alignment. So in the future, I would like to apply this concept to the real HDD case studies. And I also want to know what is the real consequence of hydraulic fracture based on the previous records. And I want to determine the threshold values for probability and consequence of hydraulic fracture, which govern the feasibility of HDD construction. And lastly, with everything collected, I want to establish the risk criteria, particularly for the hydraulic fracture. So here's my references. And thank you for listening. And I would like to acknowledge again UESI for giving me this opportunity. And I also would like to acknowledge QIC and NZERC for supporting my study. And if you have any questions, please let me know and I will answer your questions. Thank you.
Inshik, I did have a couple questions. I know this wasn't necessarily part of your paper, but when you were talking about establishing the threshold of acceptable risk, what are some of the considerations on how that is determined?
So that will have to be depending on even the same probability of failure, but the level of depth and everything has to be considered as well. And it has to be coming from larger data set. It has longer HDD, shorter HDD, deeper and shallower, and depending on which situation. So that's only talking about probability, but even for consequence, the Drew fluid is released and like what is the real consequence? That's what I was questioning. So how much time is taking longer because of this frac out, or how much Drew fluid is released, and that is what is the volume. So those type of things could be those threshold values that has to be determined, but it cannot be just only selected in mathematical way like this, but we have to actually see the construction aspect and overall project if that's feasible or not. I'm thinking we need to collect like all those construction records to make sure we have evaluated risk in all different ways in that way.
Okay, that makes sense. And then I guess a follow-up question to that is, if you had this failure of either a frac out or your shear failure, from your experience, is the project abandoned at that point, or is just going to maybe have some additional costs along those lines? It's not like it's abandoned. So can you shed light on that?
Actually, that's a good point because I'm not trying to say if frac out happens and it's the end of the world. It's actually there's many different mitigation strategies there. First of all, easy thing is you can do cleanup. Like let's say it just happened on the remote roadway on the shoulder, then all you have to do is have the plan for vac truck to come and then clean up. But for those cases with like a river crossing, and then regulators are very sensitive about if frac out happen or not, and they will really be not happy about it. And you can imagine in your subdivision, there's like a fiber optic installation or a little bit deeper pipelines. And if you keep seeing those lawns having frac out and then they're cleaning up all those like muds, then it's actually going to be affecting the reputation of the HDD itself, and it's actually not preferable because it's like it's like a human body with the like a vein, our veins. When we have like puncture in our vein, and then that spot is going to be weaker than where it didn't have that type of puncture, and it's going to keep having the blood escaping from there, and that is problematic. Same thing when we have a frag out, it will keep giving us trouble in the further installation phase until the like a reaming and the pullback. So that is the type of situation we want to make sure to prevent it, and then we don't have that situation. We need to keep going there and fix the problem with added time. So that's the idea I would say about the frag out.
Okay, that's good points to clarify. And I want to go to a question we had about about your case study that you mentioned. In the case study, would drilling the bore using the intersect method, drilling from entry and exit, mitigate high IR concerns in part C and D? And is this intersect method considered in probabilistic risk assessment?
Yes, that's correct. When we have intersect method, instead of so I can draw in here, we have this annular pressure analysis. So we have Pmax curve like this. Then it won't be Pmin curve going all the way up like this, but it will be actually starting from another point. So it has much lower envelope. So with this distance guaranteed between Pmax and Pmin, so it's going to lower down the risk. And if they're using conductor casing for each side for intersect method, then it will be actually even lower or maybe much less problematic. We all just need to consider where there's no conductor casing for those cases.
Okay, great. And then I get one more question too. We got 2 minutes left, so I think we got time to answer this. Can frac out destabilize the soil conditions under roadways?
That is possible, I think, in my opinion. I'm not like too sure about it, but mechanically, I'm thinking if there's a pavement and there's like a subbase and then existing soil, and then if there's like a frag out, and then we actually uplift those strata, then it's actually able to make the strata weaker over there. So it's not going to be just we leave it there. We might have to cut the pavement and then recover this section, backfill it properly. So I'm thinking it's actually kind of creating the uplifting condition. So it's destabilizing. That's my opinion.
Okay. All right. Well, that's good. All right. Well, I certainly appreciate everything today, Inshik. It was a very interesting subject. Glad we got a few questions. I appreciate your time and participation on behalf of UESI. And well, thank you everyone also for joining us today.
Thank you, Kyle, and thank you everyone for coming.
Everyone have a good day.
Have a good day.